Welcome to another podcast. In this episode, we're going to be taking a look at the addition principle. The addition principle is basically how to count unions, and so we're going to be looking at problems that involve set unions. The example that we have before us here is that we want to consider the set of all 8-bit strings. So remember, a string, a bit string is a string that contains either zeros or ones for each entry, and an 8-bit string has length 8. So I want to look at two different questions just to sort of highlight the differences between these two problems, and that is I want to look at how many 8-bit strings begin with 100 or end with 011. And then all I want to do is add one more possible thing to consider, or just ending in 1 for option number 2. Now, starting with the first one, so starting with number 1 here, the way that I can think of this is I want to determine the size of the set A union B, where A is the set consisting of all 8-bit strings that begin with 100, and B is the set of all 8-bit strings that end with 0, 1, and 1. So in determining the size and knowing that it's the union that I need to be looking at here, the key term is the word or. Typically when or is used, that implies that you're looking at the union. And if the word and is used or implied, then that typically means you're looking at intersections in terms of the sets that are involved. And in the case of unions, that means you're going to either be applying the addition rule or the more generalized form, which is something called the inclusion-exclusion principle, which we'll talk about in the next video. And if the word and is used, then typically you'll be applying the multiplication rule, which is been summarized in some of the previous counting that we've done, where we involved permutations and lists and things like n to the r, n factorial. Those are all multiplication rule type problems. So the first sort of idea behind these problems is to try to write it as a union. So I'm considering the set A and the set B, and I want to determine the size of the set A union B. Well, let's start with the size of A. The size of A here is, we're looking at all 8-bit strings that begin with 100. So if I consider 8 slots, and I know it has to begin with 100, then that leaves open 5 slots where there's 2 options each, or 2 to the 5th total ways to fill in the rest of the string. And so the size of A is 2 to the 5th, or 32. Similarly, the size of B is also going to be 2 to the 5th, which equals 32, because the only difference between these two would be whether I fill in the first 5 or the last 5. So for example, if I fill in the last 3 with 0, 1, and 1, then that leaves open the first 5 slots as having 2 to the 5th possible ways to fill it in. Now, the question that we have to ask us at this point is, does that mean, so does this mean that there are 64 strings total that fit this criteria? And the answer to that is no. Overwhelmingly no. And here's the reason why. I want you to consider a string of the following form. So the first 3 elements are 100, the next 2 are open, and the last 3 elements are 0, 1, 1. Then this particular string is a member of the set A intersect B. In other words, because the first 3 are 100, it belongs to the set A, and because the last 3 are 0, 1, 1, it belongs to the set B. Therefore, it belongs to the intersection of A and B. However, when we counted this number 64, we counted everything in A, there's 32 things in A, everything in B, and there's 32 things in B. But we can't conclude that the answer is 64 because everything that looks like this got counted when it was a part of A. It also got counted again when it was a part of B. Therefore, the only way to arrive at an answer here is that the answer in this case to finding A union B is to add the number of things in A to the number of things in B and then subtract out any that I counted twice. So these are the things that got duplicated. So these are duplicated counts. And a lot of times we'll just refer to them as the overlap. So you're basically subtracting off the overlap, and the question is, what is the size of the set A intersect B? Well, if I just take a look here, only two elements are left undecided, so that there are 2 squared or 4 possible strings that look like this. So the size of the set A we determined was 32, the size of the set B was 32, and the size of their overlap is 4, which means that the correct answer here is 60. So there are 60 strings that begin with 100 or end with 011. Now, as a little bit of an aside, let's consider how the second problem is both similar and different to this one. I'm asking you in this case to determine, so looking at number 2, basically the idea is to determine the size of the set A union B union C, where I'm replacing the words or here with union symbols, basically. That's the way I'm interpreting it. Now, this is always assumed, these are always assumed to be inclusive or, unless I say otherwise, meaning I want 100 or 011 or ending in 1 or all or 2 of or whatever. It's inclusive or, not exclusive or. So you got to be careful about that. Make sure you know the context of the problem that you're working on. But I want to determine the size of this three-way union, and the easiest way to go about doing that is to consider, take the sets A and B that we had before, those are still in play, and then I want to add to it the set C, which the set C is the set of all 8-bit strings that end with the element 1. So now that we have that set in tow, if I look at A union B union C and just kind of plow right ahead the way we've been doing the previous problem, I'm going to add each of the sets individually. The sizes here are the same as before. This is 32, this is 32, and what about the size of the set C? Well, the size of the set C, because it ends with the element 1, then that means there are 7 elements left open. So that is 2 to the 7th or 128 possible things in the set C. And so if I went ahead and added all those together, I would get a total of 192 things, which is going to be incorrect because if you look at this, adding all those together, we still have possible overlaps. In other words, there are things that belong to the set A that also belong to the set B, so they would get counted twice. Or there might be things that get counted 3 times, right? It's conceivable that you could have a string that ends with a 1, ends with a 011, and starts with a 100, in which case that string would get counted 3 times. And so we've definitely got overlaps here. So how do we deal with the overlaps? Well, the idea is I'm going to have to subtract out all of the two-way intersections. So the way I typically do this is subtract and then in parentheses here, A intersect B, A intersect C, B intersect C, the sizes of all of those. And so let's think about this for a second. A intersect B, what does that look like? Well, that would be strings that have both A and B as properties. We did that in the previous one, right? So there's 2 squared or 4 of those. What about A intersect C? So A intersect C would look just like A intersect B, except instead of having 0 and 1 decided, only a 1 would be decided, leaving 4 open slots here. So if we're leaving 4 open slots, then there would be a total of 16 choices. And then finally, B intersects C. So B intersects C would be 0, 1, 1, and then 1. And it wouldn't matter if any of the first 3 had been chosen. So if I'm looking back over here, I could leave, in this case, 5 open slots. Understand that because C is a subset of B, the size of B intersect C is just going to be equal to the size of B. They're going to overlap everywhere that C overlaps, and so you're going to have just as many openings as you would have normally for B because, excuse me, I wrote that backwards. B is a subset of C. There's more things that end in 1 than there are that end in 0, 1, 1. So B is a subset of C, which means that when you look at their intersection, you get the smaller set, which is B, and the size of the set B we've already discussed is 2 to the 5th, or 32 different things. Finally, there's one more thing to consider here. Have we taken out too much? I added in A, B, and C, and then I took away any overlaps. But what if I had an element that belonged to all 3? So let's think about the set A intersect B intersect C. That string would have 0, 1, 1 and 1, 0, 0. Now let's talk about that string for a second. It got counted in A, it got counted in B, and it got counted in C. So it's been counted 3 times. It's also in A intersect B, so it gets subtracted once here. It's in A intersect C, so it gets subtracted once here. And it's in B intersect C, so it gets subtracted once here. So it was added in 3 times, and it was subtracted out 3 times, which means that strings of this form aren't actually being calculated in the final total. They've been added in and subtracted out an equal number of times, which means that I have to add back in the possibility of a string containing all 3 sets. And A intersect B intersect C is just going to be 2 squared. As you can see, it leaves 2 open slots, or a total of 4. So adding this example up, we have 32 plus 32 plus 128 minus 4, 16, and 32 plus 4. So this brings our total here. Let's see, 192 minus, we're going to throw out the 52 duplicates, but we threw out 4 too many. So we end up with 144 for our answer here. So there are 144 strings that end with 100 or 011 or potentially end in just 1. And so it's a much larger number than the 64 we looked at with before because we're including a lot of extra strings that could end in a 1, whereas before they had to end in just 011. So this is something called the addition principle, and I'll sort of point you to the basic formulas that are being used here. This is the addition formula for 2 elements, and then the addition formula for 3 elements is a little bit more convoluted, but it involves this piece, this piece, this piece, and this piece. That is the addition rule for 3 elements, is those 3 that we use there. Basically, you add in all the single sets, you subtract all of the 2-way intersections, and then you add back in the 3-way intersection. Alright, this has just been a basic introduction to the addition principle. In the video that you're going to follow up with next, it's a video that talks about how to generalize this rule to a much larger number of sets, and it's something called the inclusion-exclusion principle. Alright, thank you for watching.